this video, we'll look at how to calculate a vector product using the components of the two vectors. Remember, in the previous video we defined the vector product on two three-dimensional vectors using the following formula. A cross B equals the magnitude of A times the magnitude of B times sine theta n, where theta is the angle between the two vectors and n is a unit vector perpendicular to both A and B. However, it is also possible to compute the vector product using the vector's components, and in doing so we obtain an explicit answer in component form. So if our two vectors are A equal to a1i plus a2j plus a3k, and B equal to b1i plus b2j plus b3k, then we can define A cross B as a2b3 minus a3b2i minus a1b3 minus a3b1j plus a1b2 minus a2b1k. It's possible to prove that this definition is equivalent to the first definition, but for the purposes of this video we'll just take it as a given. Now, the definition looks quite long and difficult to remember, so let's look at a method for remembering it. The formula is in fact equal to the following matrix determinant. So that's the determinant of the 3x3 matrix that has as its first row the vectors I, j and k, its second row the components of A, and its third row the components of B. To prove this is the same thing, let's calculate this determinant. So we take the first entry of the first row, which is I in this case, and then we block out the row and column this entry is in, and times the entry by the determinant of the 2x2 matrix that remains. So that's A2, A3, B2, B3. Now, we move to the next entry in row 1, which is J. But remember, we must alternate the sign, so we have minus J. And then we multiply again by the determinant of the 2x2 formed from deleting the row and column J is in. So that's A1, A3, B1, B3. Finally, we take the third entry, K, and this time we're back to plus, and we times by the determinant of the matrix made by deleting this row and column. So that's A1, A2, B1, B2. So, let's calculate all these determinants. We have I times A2B3 minus A3B2 minus J times A1B3 minus A3B1 plus K times A1B2 minus A2B1. This is indeed A cross B, as defined above. Let's look at an example. We'll put the two different definitions up here for reference. Let's take A equal to 2i plus 2j plus 0k and B equal to minus 2i plus 2j plus 0k. On a graph, these two vectors look like this. Let's make a few quick observations. Using Pythagoras' theorem, the length of A is the square root of 2 squared plus 2 squared, which is root 8. Similarly, the length of B is also root 8. Also, hopefully you can see from the diagram that the angle between A and B, theta, is 90 degrees. So first of all, let's use the first definition. So A cross B is root 8 times sine 90 times n hat. But what is n hat in this case? Well, using what we discussed in the previous video, we can deduce that n hat would be the unit vector pointing in the direction of the z-axis. Now, simplifying gives 8, that's root 8, times 1, that's sine of 90, times n hat, which is 8n hat. But if n hat is a unit vector pointing in the direction of the z-axis, then n hat is in fact just the vector k. So this equals 8k. Now let's use the second method. So A cross B is equal to the determinant of this matrix, ijk. 2, 2, 0, minus 2, 2, 0. This is equal to I times, well, it's 2 times 0 minus 2 times 0, so 0 minus 0, minus j times 2 times 0 minus 2 times 0, which is also 0 minus 0, plus k times 2 times 2 minus 2 times 2, which is 4 plus 4, since the two minuses will cancel out. So this is just 0i minus 0j plus 8k, which is indeed just 8k, as we hoped.